Today on Xenodilidon, I'll be talking about Tesla coils and Tesla coil accessories. Now, this video will be focused around two different circuits, the Slayer exciter and an interestingly modified version of the zero voltage switching oscillator, or ZVS for short. Now, this is more of a hobbyist video, not enthusiast one, so don't expect any big, powerful Tesla coils. However, this is still a Xenodilidon video, so expect interesting Tesla coils. Since this is mostly an educational channel, I'd like to go ahead and draw some archaic circuit diagrams and explain to you how the components in these circuits come together to make fully functional Tesla coils. So let's start by talking about the Slayer exciter. And to start off with, we need a Tesla coil to power. So I'm going to go ahead and draw that. And that's comprised of two coils, the primary and the secondary, thus making it Tesla's coils. The primary is the thicker gauge wire with fewer turns, so I'm going to go ahead and draw that. Keep in mind that it's thick. Make a couple of turns. Let's do 3 loops because that's what Tesla would have wanted. And then we got it down like that. And then we're going to draw the secondary. The secondary is the thinner gauge wire. It has more turns. So start over here. I'm going to scribble back and forth a lot to signify the many turns of coil we have on our secondary. There's the top out like that. So the main thing about Tesla coils is you want to get them to resonate. The transformers, they need AC or pulsed DC. In this case, we're going to use pulsed DC, and that's controlled by a semiconductor. In this case, it's going to be an NPN transistor. A lot of these Slayer exciter circuits use a 2N2222. That transistor has 3 legs coming off of it like that. The input of the power goes into the emitter. So I'll draw E here. The state of the transistor, whether it's conductive or not, it gets controlled by the base. And then the output gets controlled by the collector. Output is the collector. It is an NPN transistor, so I'm going to go ahead and put that on negative like that. So our electrons are going to be coming in through here when the transistor is turned on. And then from there out to the primary. Now there's a return path to positive from the primary. So let's go ahead and draw that. That's our return path. And we'll say that this goes up to our power source right there. In order to turn on the transistor in this case, we need a positive potential, positive bias on the base, and we have that potential applied through a resistor. Resistors limit current. Usually it's a 22K resistor, but you can play around with this value, get slightly different results depending on the transistor you use. But I'm going to put 22K as a good reference. Now in this situation, this configuration, the transistor would be turned on. So that means that we have an electrical current flowing through the transistor and flowing through the primary coil. Now we need a state of changing flux in order for the secondary to pick up that state of change, step up the voltage. So how do we control the oscillation in the primary circuit, the primary coil? Well, we use the secondary as our feedback coil. So I'm going to go ahead and I'm going to draw a wire going to here, right to the base of our transistor. And because we have an oscillating circuit, an oscillating secondary, half the time the secondary will be positive up here, negative down here. Half the time it's going to be positive down here, negative up here. So the electrical bias is always flipping like this on each side of the secondary. When the secondary is negative, so down here it's negative, it'll send a negative bias to the base of the transistor, which overrides the current that's going through this resistor here, which shuts off the transistor. Now we have another state of change when there's no more power being applied, magnetic field collapses, this flips around. All of a sudden, we don't have negative here anymore. We have positive. Of course, positive is once again going through the resistor here. Turns on the transistor, and the whole process repeats. So it's the feedback from the secondary coil, which controls the oscillation and the state of the transistor being on or off. In a lot of the Slayer exciter circuits, you'll see an LED. So let's go ahead and draw that in real quick. I'm going to go ahead and use purple. Well, there's an LED that's located on the emitter, the input, and right here. So we're going to draw that. Come together, draw an LED. And an LED in this case is not only used to indicate whether or not the circuit is working, but it's also a clamping component. And this can have some effect on how the transistor operates. So as there is a current being produced by the secondary, the current flows through this wire, goes to the base, but it'll also go to the LED. And once there's enough voltage to start conducting through the LED, it clamps the voltage at that point. And that's the amount of voltage that is allowed on the base of the transistor. We can actually change the voltage going to the base. Once again, as I said, it has some effect on the transistor. So you can actually get a little bit more performance by selecting the right LED. And in a lot of these cases, you don't even need the LED because the current and the voltage coming off the secondary isn't going to be enough to damage the transistor. So this part we can consider superfluous. So we don't need the LED, but it's a nice protecting / indicating part of the circuit to have. By the way, I do believe that the anode of the LED goes here. So we put A, and then the cathode of the LED goes on the positive, negative. I think it's backwards. You put it on, and if it lights up, it lights up. But you don't need it. So not going to pay too much of importance to it. Over here, I'm going to continue to wire up like this. And then I'm going to also make a recommendation to put a capacitor really close to the transistor. So I'm going to go ahead and draw that in. Right here, draw a purple capacitor. Done. And then another connection here to the capacitor. Now adding a capacitor in these circuits can drastically increase performance. Why? I'm going to go ahead and I'm going to take these wires and we're going to extend these wires real long. Like that. Good old long wire. That's going to go to whatever power source we're going to use. Go ahead and take this, make it equally as long. And you got these long wires flying whatever. The primary in this case, and in most Tesla coils, is going to be real low impedance, often in like the milliohms. So there's going to be a high demand for current going through the primary. However, that's only for a brief moment. So if we have higher impedance, long wires here, and lower impedance wire here, lower resistance, the amount of current that's going to be initially supplied just from the wires is going to be really, really low because you have all the voltage drop going through the wires. However, if you have a capacitor over here and it's very close to your circuit, you have an immediate source of current that's going to be able to be provided by the capacitor, instead of the current and the voltage having to go through the resistance of all the wires. So this can increase the performance of your Tesla coil significantly because it really does provide that immediate on-demand boost of current to drive your Tesla coil. Very important. Let's go ahead and see some Slayer Exciter Tesla coils. Ah yes, the simple and underappreciated Slayer Exciter Tesla coil. And while many enthusiasts wouldn't be all too excited by this little birthday cake candle-sized Tesla coil, it's still pretty neat. Has a little neon light on the top, which lights up pretty nicely, and it can even light up this fluorescent bulb with little effort. Other than that, it really doesn't do too much. But that doesn't mean that the Slayer Exciter Tesla coils don't have their place. back, the circuit can be very useful, such as in this little magic marker that uses a 2N2222 transistor based Slayer exciter circuit. Another interesting thing I did with the Slayer exciter circuit was I made these kits for these kids that my girlfriend knows. We'll go ahead and put together one of these kits real quick. I'll show you how that turned out. Start the music. Ta-da! See, that turned out pretty well. I don't have a USB plug on the desk, but I do have another identical Tesla coil, just like that. Let's go ahead and plug that one into a battery. Use just one of these little connectors here. And through the magic of wireless power transfer, we have this Tesla coil lit up. Even it's not plugged in, because it's getting the energy from this Tesla coil. Poor time to burp. And it lights up source and bulb quite nicely. No problem with that. Pretty cool. The kids will love it. You'll also notice that there are these little hoop holders, and that's where some of the accessories come in. I'll talk about these accessories a little bit later, but go ahead and show you some of these. I've got the little neon lamp accessory, just like that. I have another fluorescent little lamp indicator accessory, like that. I have a little fluorescent tube accessory. I take that to light this a little weirdly. There we go. Nope. There we go. And I got this LED accessory. It has two LEDs. And that also lights up too. I'll turn the light off. See? Isn't that neat? That right there is a functional night light. Functional night light. I love it. The kids will love it. But if you're not impressed by that, hold on to your socks. I have some really impressive Slayer exciter use to show you. We all know there's a wide range of size and performance, and while many Tesla coil enthusiasts enjoy making larger and more powerful Tesla coils, I find myself in the category of individuals who enjoy making miniaturized things. So I use the Slayer exciter circuit to make this 37mm tall Tesla coil. And it does work. Go ahead and plug it in. I'll use a helical compact fluorescent bulb. You can see the bulb lights up pretty nicely. Now, even though this Tesla coil does work, there are some things about the design that I do not like. I don't like how I filled this lower section in with the hot glue, nor do I like how the epoxy wicked into the top load of this Tesla coil, made it look like it was filled with caramel. And these were design choices I deliberately avoided when I made what could possibly be the world's smallest Tesla coil. When measured in height, this Tesla coil is an astonishing 30 millimeters tall, and yet it is fully functional. Let's go ahead and plug it in. If you don't think that is an awesome use for a Slayer exciter circuit, I don't know what to tell you. But I think this is one of the most awesome Tesla coils I've ever put together. Before I get into discussing the modified zero voltage switching driver, I'm going to go over the Slayer exciter circuit in a little bit more detail, how it's configured, how to select different parts, its pros and cons, and some basic Tesla coil tuning that applies to all Tesla coils. Let's take a look at the circuit. So just like in the crude diagram I drew earlier, it starts off with a capacitor, and that is on the input side of your circuit. The capacitor really does help. It provides the immediate source of inrush current for the primary of your Tesla coil. So very important. That way you don't have to fight the resistance of your power input wires. Really does help. From there, I have this transistor. Now, the transistor I'm using for this is a 2N2192A. If you have a stash of NPN transistors, whether you salvage them or collect them like I do, I encourage you to go through your stash of transistors, see if you can find one that works real good. If you want to build one of these, that's how I found out that the 2N2192A works very well for this. We have the LED here, and the LED is just for clamping the voltage and current. It goes to the base of your transistor. It shows you that the circuit is working and helps protect your transistor. On the positive side, we have this resistor that comes up like this, connects to the base of the transistor, that turns on the transistor. And to turn off the transistor, we have the changing polarity, that alternating bias that comes through the base of the secondary here. When this is negative, transistor is off. When the polarity bias flips, it helps turn on the transistor, as well as the positive coming from the resistor here too. Now, if you're playing around with different transistors, I'd highly recommend that you get a 50 kilo ohm potentiometer. You set it to 20 kilo ohms and you put it in place of where the resistor would go. That allows you to dial in the precise resistance needed to best drive the transistor that you chose. Another thing to note is that if your Slayer exciter circuit does not operate, flip the primary wires. So for example, if this didn't work, I'd unsolder this, I'd flip this wire around. So this is here and this is here, because the coil needs to be in phase to provide the right signal from your secondary to turn on the transistor, turn off the transistor too properly. So that way it works. So yeah, be mindful of that. The polarity and the phasing of the primary, very important. So if yours doesn't turn on, flip those wires. Let's talk about the pros and cons. Now, the Slayer exciter circuit is a really easy circuit to build, and if you're just running things like light bulbs, it's a fantastic circuit for that. But the Slayer exciter circuit is not known for its arcs and sparks, so I wouldn't suggest expecting arcs and sparks from your Slayer exciter. Go ahead and talk about pros, cons, and tuning. All right. Well, talk about cons. There's a con right there. Turn off the light. Now, the more you load a Slayer exciter, the less output power you'll get, respectively. So, if I put another light here, I turn it on here. Yeah, they're weird when they're loaded. They get in funky resonance modes too. But let's talk about some basic tuning. And once again, this applies to every Tesla coil. There is a relation between the oscillation in your secondary and how it reacts to the primary. So changing the location of your primary in retrospect to your secondary can change the performance of your Tesla coil significantly. There will be a particular hotspot on your secondary that your primary should be closest to. Watch. All I'm going to do is change the position of the secondary in the primary. Go ahead and move it. Come on, light up. There we go. And then depending on the location, you'll eventually find a spot of optimal performance. So it looks like about a quarter of the way up is where I get the optimal performance out of this. Like that. A downfall to show you about the Slayer exciter circuit is that the output frequency can change depending on the length and configuration of your power wire. So if you add any kind of capacitance or length on your input wires, you can also change the performance of your Tesla coil. So you might think like this: you have a great running Tesla coil, you take it off the battery and you choose to connect it to an AC adapter. That changes the length of the wire, and all of a sudden your performance goes away. So that's another thing to watch out for too. And you seem to have pretty good performance. All of a sudden your performance is gone. So the Slayer exciter really does kind of work best with a power source like a battery very close by. Another thing, as I said, they can kind of get into weird resonance modes too. So see if I can get this one go into a weird resonance mode. Yep, like that. You can see how it's not as bright. And if I disconnect it, reconnect it. Come on, come on. Yeah, there we go. Now it's working. They can get into weird, funky resonance modes. Cooling the transistor does help if the transistor does get hot, but yeah, the Slayer exciter. It's an easy circuit. It's a little bit of a fickle circuit. So, as I said, some things to watch out for. You can also change the LED, and that can sometimes squeeze a little bit more performance out. But trying to maximize the performance of a Slayer exciter, add a capacitor, watch the length of your input power wires, find the optimal position for your primary in comparison to where the secondary is, and you should be in good sailing with your Slayer exciter Tesla coil. Now let's discuss the modified zero voltage switching Tesla coil driver. And if you're looking for performance in a simple circuit, this is one of the best Tesla coil drivers you can make. This is shown to me by my friend JP. I'll link the original video down below. It's really cool. So you'll need a few things, mostly 2 MOSFETs and 4 diodes. But first, let's go ahead and draw a Tesla coil. So same thing, I'm going to start with my primary. So well, let's do it a little bit smaller so we have some more room here. Same thing, we'll do 3 turns. 1, 2, 3, like that. All right. And I'm also going to draw the secondary. Oh, base of the secondary, squiggle, squiggle, squiggle. All right, so that's our secondary. Now let's draw 2 MOSFETs. So I'm going to draw them down here. 1 MOSFET. That's another MOSFET. Here is the drain of each MOSFET. The source. And then the gate. So those are the 3 connections to our MOSFETs. The sources get connected to the same negative side of the circuit. So we're going to go ahead and draw that in. Just like that. And the sources of your MOSFETs are your input. So these are NPN channel MOSFETs. Enhanced mode, if you want to get particular. All right. And then from there, we're going to have to figure out positive. So let's go ahead and draw positive side of the input like this. Now, the positive in this circuit does not get directly connected to the primary of your Tesla coil. Instead, I'm going to go ahead and connect the drains like this. Now you might be thinking, we only have the negative side of the circuit being able to be connected to the primary. Doesn't work. Well, that's because we'll be bringing either a center tapped inductor or two separate inductors. And what an inductor is something like this. And notice it has one loop of wire on it, so it's not a transformer. So we're going to go ahead and draw two inductors now. I'll use orange. So there are two inductors, and they go between the positive and the drains of the MOSFET. So I'm going to go ahead and do that. Little circle, inductor wires, and then other side of the inductor like that. And we'll have another inductor right here. A little circle, wire to positive, and then over to the drain of the MOSFET once again. So in this circuit, the goal is to turn on one inductor, have the other off, and then flip them. So that makes the magnetic field in each inductor oscillate. When one is on, one is off, and they dance back and forth. And it's the magnetic field generated in these inductors that gets fed to the primary of your Tesla coil. So how do we control which MOSFET is on? Here's part of the circuit that I'm not 100% exactly sure why it works, but I know that it does work, and that involves 4 diodes. I'm going to go ahead and draw those like this. So it's one diode. We'll draw another diode, say down here. Good place for it. Draw one diode over, let's draw it over on this side. Actually, it'll be a little easier to understand. So one diode here, one diode here. I'm going to go ahead and mark the cathodes of those diodes with purple. So that's cathode side of the diodes. Go ahead and draw some connections with blue. So these two connections right here, the anodes, they get connected to the ground here. And then you have these cathodes up here. Those cathodes get connected to positive like this. They can connect this one also over to positive like this. And then between the two diodes, they're actually connected. So we've got a connection like this between those two. And we're not connecting these to the positive. So I'm going to jump over that like this. And then like that. So the same thing like the Slayer exciter, we need to also turn one MOSFET on. And we're going to do that the same way we did with the Slayer exciter. And that's by putting a resistor on one of the MOSFETs. Because once we start the oscillation, the ringing of the actual coil will continue the oscillation. So I'm going to start over here with this gate. We're going to have this MOSFET turn on to start the oscillation. So I'm going to go ahead and do that. I'll put a resistor to positive. And the resistor that I like to use is anywhere from 1K to 5K. I'm going to put a 5K right here. But you can play around with this resistor value and get the results you need. Next thing I'm going to do is I'm going to connect the gates of each MOSFET to where the meeting point of each diode is. So from here, I'm going to connect this MOSFET gate up like that. We got this MOSFET gate here, and I'm going to connect it to this point right here between these two diodes. Just like that. Get that little easier to see there. There you go. Okay. So we're going to do something a little different, but very similar to the flare exciter. We're going to use the secondary of the Tesla coil as our feedback coil, and we're going to do that through a gate drive transformer. A gate drive transformer is a very simple type of transformer. We're going to be using a 1-to-1 ratio like this. So if you put in 2 volts in this side, you'll receive 2 volts from that side. But what this allows us to do, say we connect this side to ground, and then we have a changing bias on this compared to ground. Well, that gives the gate drive transformer a changing magnetic field. And then, of course, on these 2 wires, we would also have a changing polarity that is induced magnetically on the transformer. So keep this in mind. I draw a gate drive transformer now. I'm going to choose purple for my gate drive transformer. So where's a good place to draw that? Decisions. Let's go ahead and draw it like this. No, off there. Not connected to that. I'm going to do a circle here. And I'm going to do this side in purple, indicating 1 winding on the gate drive transformer. And I'm going to run that to there. The other side of this gate drive transformer, we will be connecting to ground. So I'm going to go ahead and connect that to ground. Over positive, connected to ground. Let's choose red for the other side of the gate drive transformer, because we'll be using it to turn on the gates of the MOSFET. Also, by default, turning them off. So here's another coil on the gate drive transformer. One side of the gate drive transformer will go to one side of the circuit and on the MOSFET gate. So that'll be connected to this side right here. So that's very carefully and not confusingly draw that connection somehow. Well, this is more difficult than it seems. Let's go this way. Let's go this way over here. Okay. We're just gonna forget that's there, and we're gonna connect it like this. Perfect. You don't run into that on a circuit diagram. So new situation, but we got it. One side of the gate drive transformer connects to one of the MOSFET gates. Of course, the other side of that then gets connected to this MOSFET gate. So the changing polarity, changing bias on this side of the transformer, because we have an induced magnetic field on the gate drive transformer, as the secondary oscillates, changes its polarity. That flipping polarity on the gate drive transformer will turn one MOSFET on, because this side, say, would be positive, and it would turn this MOSFET off, because then it would be negative. And then when this flips, its polarity, the bias changes. It changes in the gate drive transformer. All of a sudden, this side would be positive, this side would be negative. So that's how this circuit works in a nutshell. Once again, same thing with the Slayer exciter. Adding a capacitor real close to our transistors helps immensely. So we're going to go ahead and draw a capacitor here. And then your whatever power source you're using would be connected here. Same thing like you saw with the LED on the transistor between the emitter and the base. You can use Zener diodes or you can use LEDs to clamp the voltage and the current that's generated by the gate drive transformer. You can clamp the voltage going to the MOSFET by throwing a Zener or an LED across the source and the gate of the MOSFET, and it'll clamp the voltage here. So if you're going to put any kind of protection device, that would be the place to put it. But this is circuit in a nutshell. And now that I have your attention, let's discuss choosing components. Many of you might have questions on what parts to choose, and frankly, I really can't help you with that because all of the parts are interdependent on one another, as this is a self-resonant system, and that really does depend on what you have to work with and the configuration of those parts. So if you ask me what kind of wheels do I need, and you don't know what kind of car you have, I can't tell you what kind of wheels you need. So what I'm going to do is I'm going to go over some of the components. I'm going to explain their electrical and physical characteristics. And I'm going to tell you how they all link up together. Hopefully that'll help you select parts for yourself. The basics of a Tesla coil is it is a step-up transformer. So the first thing to pay attention to is the ratio of coils. So here I have a transformer from a CCFL inverter, and is a step-up transformer. So say we have 10 turns here of pretty thick primary wire, and we have much thinner wire here, but we have 20,000 turns. So this would be a ratio of 1 to 2,000, and if we put a volt in here, we get 2,000 volts out here. It's not quite that ratio. I think this is a 12 to 2,000 volt output CCFL transformer, but the goal really is to keep the primary count down. So usually 3 or 4 turns on the primary, and then for the secondary, you want as many coils as you can get wrapped on. Let's take a look at these two secondaries real quick. And you can see that they're pretty different. The bottom coil has pretty thick wire, and we have about, 100 turns on there. Meanwhile, the wire used on this one is much thinner, and we have many more turns. The impedance, or AC resistance of this one, is about 4 ohms. And this one is about 100 ohms. And I want to say there's got to be about 5 times more turns on this one than this one. So we get much higher voltage from this than this. We get more current from this one though. So it's a trade-off in a transformer. In this case, we're trading current for voltage. So let's take a look at some of these smaller secondaries. So here again, we have a secondary with a really thick wire, not that many turns. So this would be poor coil to use for a secondary in a Tesla coil. And it gets even more difficult when you're building small Tesla coils because you still do need that ratio, which means you need to figure out how to get all those turns on that coil. And that involves using some very thin wire. Yeah, camera doesn't even want to focus on it. Imagine what it must feel like to wrap these things. Hours of entertainment, I tell you. So the goal really is to get as many turns on your secondary as you can possible. Another thing to discuss is the ratio size between your secondary and your primary. As far as copper mass, you want to kind of have roughly the same, a little bit more copper mass on your primary than you do on your secondary. There's no point in wiggling around electrons in your primary that have no place to go as far as delivering the energy. So that's one thing. Second thing is the height ratio. I pretty much like to stick to a ratio of 7 to 1 or under, and that means that, say for example, if this is 7 inches tall, this would be 1 inch, and you don't want to go any higher. You don't want, say, a 10-inch tall secondary and a 1 inch tall primary. I'd like to say keep the ratio anywhere from from 3 to 1 to say 7 to 1. Anywhere between there is good, depending on how tall your secondary coil is. So just some tips there about secondary and primary configurations, and the size determines the wattage. Let's take a look at inductors. Now, these are mysterious devices to a lot of people. Their properties really do come down to two things: what they're made of and how big they are. You have to treat them as bells. So depending on what a bell is made out of, it can ring higher or lower, and depending on its size, it can ring higher or lower. Same thing with magnetic components like inductors or transformers. These characteristics are determined by the materials and the size. We're not going to use any steel core laminated kind of transformers. This is all going to be different ferrite materials, and ferrite responds pretty quickly, but we still have size to look at. So we have inductors like this. We have a nice, kind of tone. And if we have inductors like this, we have a nice little kind of tone. And if we use smaller inductors yet, higher frequency tone. So you have to think about these as bells. And if they're big, you can store a lot of energy into them, but you can't retrieve and store that energy very quickly. Whereas if they're smaller, they're faster. You can't store as much energy, but you can deliver it in and out of the core much quicker. If you're looking for really tiny inductors, you can find those, and I've used these for gate drive transformers. You can find these little inductors, cores, inside of the Ethernet filter, that's isolator box. And I got this off a laptop. But yeah, very tiny toroidal cores in there. Very useful for the miniatures. The other thing that determines the characteristics of an inductor is the geometry of the actual core. So you have open core, you have closed core. If you take a look at these two rod inductors, you can see that the ends are open, so this is kind of like a barbell. So this is open. Same thing with this. This is an open side. And you have closed cores. So this is a closed core, a toroidal core, and you have this also a closed core, and this is an E core. And the upside to a closed core is that you have a little bit more magnetic flux that's wrapped inside of the core, a higher level of saturation, and you can deliver that flux in your coil. Or like, for example, a gate drive transformer, you can deliver that flux with a bit more current than if it was an open core. In fact, they gap transformers in the middle here to limit the amount of current that can be delivered from the primary to the secondary by limiting the magnetic flux and how closed that core is. So yeah, if you want to deliver energy and move energy in magnetics, have a large core, closed core. If you want to deliver real fast and not a lot of current, you have a small core and open core, and you can choose between those characteristics. But something to think about: the size and amount, or small and quick. A lot of magnetic field stored slow, a little bit stored fast change state. Take a look at MOSFETs. Now, MOSFETs are the confusing things for a lot of people too, and I'm going to draw a little diagram, try and help explain why that's confusing. Now, a lot of these Tesla coils will operate with an input voltage anywhere from 5 to say 20 volts. You don't really want to go higher than 20 volts. But what I'm going to do is I'm going to draw a triangle. And that means that we get to play the game of pick 2. Up here, we have current. So, because these are step-up devices, we are trading current for voltage. Down here, we have speed. So, how fast can the MOSFET change its state? And over here, we have heat production. How hot will the MOSFET get as it's operating? You get to pick 2. Can't have all 3. Well, maybe you can with GAMFETs, but we're not talking about those. Talk about a good old metal oxide silicon field effect transistor. Now, to understand what the issue is, let's go ahead and quickly draw a little diagram of a MOSFET. This is an NPN enhanced mode MOSFET N channel. I'm going to draw N here and here. We're going to go ahead and put our positive semiconductor material in here, like that. Done. And then we have our source, and we have our drain. Now the goal is to get the electrons that are coming in on this side across the junction out of the drain. So what we end up doing in this case is we want to put a positive bias up here, now opposite the track. So you got the negatively charged electrons. They want to be pulled through across the junction up like this. So what we do is we put a positive field up here, hence the term field effect. When you got like a bipolar junction transistor, it actually takes current to drive the junction. In a MOSFET, it doesn't take current, it just takes voltage. You're just placing a field on there. So there's an insulating barrier of sorts, and that's made of metal oxides, hence the name metal oxide. And then I'm going to draw the gate on the top. So that's the gate. Now when this has a positive bias, as I said, it draws the electrons in through the junction. When I have a negative bias, it repels the electrons, drives them out. It's no longer conducting. That's how it works in a nutshell. Now, there's something called gate capacitance. So let's mark that down, so that way we remember it. Not so much space down here, so I'm going to write gate cap, or gate capacitance. Now, this has to do with the size of the MOSFET structure. If the gate is larger, it takes more time to deplete the electrons and to add electrons on that area. And this changes the reaction speed of the MOSFET, which changes its on-state characteristics with frequency. So, a MOSFET can have a low on-state resistance, which is what makes them very good. The problem is they don't change instantaneously. So, say for example, when they turn on, they're 0% conductive, and they go up like this, raising conductivity, and then they're on. And if they're real big MOSFET, they'll take a while to reach that point. And if there's a real small MOSFET, they'll go up real quick and get conductive almost instantaneously, because it doesn't take that much time to deplete or add electrons in there, change the state of the MOSFET. The area that you want to avoid is any area in here. You do not want the MOSFET to operate in what's called the linear region, and that's when the MOSFET is kind of turned on. During that state, it's not fully conductive. It's a little bit more resistive than the full on state, so therefore it gets warm as it dumps the energy as it's in that resistive state into something, turns it into heat, but we get heat. Now the other catch is the smaller you make this junction, less current it can pass. So if we have big junction, that means it's going to be slow, not going to be fast. And if we try and run it fast, it's going to generate a lot of heat, but it's good for a slow transformer, a lot of energy. If we have a very fast transformer, if we use a fast gate, we're not going to have as much current because it's not going to be as big. But we're also not going to generate that much heat because we're not going to be in the linear conducting region for as long as the MOSFET is changing its on or off state. So, with that in mind, say we have this MOSFET right here. It's a big MOSFET. It'd be suitable for a much larger Tesla coil than, say, this. Much larger. So lots of current, not very fast. It generates a bit of heat. Let me put that over here. This one right here, it's a pretty big MOSFET, has a decent amount of current, a little faster. So you can put that here. Another type of MOSFET. That one's probably pretty quick, not so much current, not so much heat. So we're going to put that down here. Take this one, decent amount of current, decent amount of speed, overall good general MOSFET size. They're like a 30 volt, 50 amp MOSFET. So lots of current, pretty fast, can get kind of warm. This one right here, not so much current, but it's very fast, not so much heat. So they put that over here. And finally, we have a little SOT 23 that bounced over here. Very fast, not that much heat, very not that much current. So that bugger would all be down right over here. So we can get kind of an idea of where we're going to be by the size of the MOSFET. So when you're choosing a MOSFET, you want a MOSFET that's pretty quick, has a decent amount of current, and won't generate a lot of heat. So sometimes it's better to use a smaller MOSFET than a bigger MOSFET. It's just how it works. Let's take a look at diodes. Now, you can use a signal diode, or you can use a Schottky diode. The biggest factor is how much current are you feeding to your gates, and how fast you need it to go. So, if you have a very slow Tesla coil, using a big primary, big secondary, lots of current, you want to use a big diode like this, Schottky diode right here. Medium coils, you can use diodes like this, decent amount of current, say 1 amp, pretty quick, but not the fastest. And for small Tesla coils, you want really fast, say, signal diodes, and you don't need to worry about all the current because a little coil like this, it's not going to generate a lot of current. So, but you need the fast response rate. Say coils like this coil right here, they operate in the 2 megahertz range, with coils like this can operate in the 9 to 10 megahertz range and 20 megahertz range. So you want a really fast responding diode. Otherwise, they generate heat and they don't work very well either. So that's kind of how all the components work and interact with one another. Now I also want to say one thing I remember about inductors. In this circuit, you can use either 2 matched inductors or you can use a center tapped inductor. So for example, say I use 2 matched inductors. And I take and I trade them together. So, they're like this. So they're like this. So that'd be my my center point with positive goes, and then this right here would be what my gate or my drain of the MOSFET attaches to, and then these two would go out to my primary. But I can also use 1 core. So I got these 2 leads right here, and I got my center tap here. And this would connect to positive. Each one of these would connect to the MOSFET drains. And I have 1 part instead of using 2 discrete inductors. So that's something to keep in mind as well. Now that I've discussed all of the parts, kind of what they do and how they work with one another, let's go ahead and take a look at some real working modified 0 voltage switching Tesla coils. When it comes to making a simple yet high performance low voltage input Tesla coil, the modified 0 voltage switching circuit pretty much the way to go. However, it does have its own drawbacks, and well, many high performance things do. Now it's low voltage, so this thing only runs at like 10 volts, right? Well, it runs at 10 volts at 10 amps. That's 100 watts. Yeah, 100 watts out of this little bugger. Oh, it's a decent amount. And 10 amps is a decent amount. So there are some problems. First problem is because you're running that much current, the parts inside can get quite hot. So I got a little heat sink down here. The inductors can get warm. The primary can get warm. And if that happens, add turns, what I found. But yeah, this is an indication of another problem, and that is that you get corona that builds up on the primary and on the secondary on the inside. That's due to coupling, just high frequency AC coupling. All that corona is generated. Let's see if I show you that. Where are we? 8 volts. All right, so here's 8 volts. That's at 5 amps. I'll bring up the voltage and the current until we get corona on the primary coil down here, and then I'm going to turn it off right here. There's lots of layers, so I got a little bit of time to be a little bit cautious, but you'll see what could be catastrophic if you're not watching for it. Here we go. And then we'll probably hit about 10 amps. 11 volts, 15 amps. Oh, that's scary. Oh, and there it goes. No. Yeah. Make sure you don't skimp out on the insulation between your primary and your secondary. That's quite a lot of insulation that I have already. I want to say about 3 millimeters, 2.5, 3 millimeters of insulation. And yet, corona is still generated here. Now, that's not breakthrough. That's just you got corona on the primary coil. And if you're not careful, that'll burn through your insulation and then start burning into your secondary. So you want to be careful. You want to avoid that. That's the end of a lot of good Tesla coils. Let's take a look at a couple more. So I made this one, and this surprisingly uses SOT23 MOSFETs. So very small MOSFETs, little diodes, little inductors here. You can see the MOSFETs at all. Probably not. But yeah, they're SOT23. Small little MOSFETs. Yeah, there it is right there. And these are the 5.6 amp. I'll list the part that I used in caption. Nice little Tesla coil. Very fine wire. It's actually astonishing how much performance you can get out of this little SOT23 MOSFETs, quite honestly. And the reason why you can get so much performance out of them is because they switch so quickly. That's why there's no heat sink on here. I am clamping the voltage going to the gates with LEDs, and unlike the Slayer exciter, the anode of the LED goes on the gate and the cathode goes on the source. So it's not reverse bias like it is on the Slayer exciter. Totally different circuit in that aspect. All right. Good old lithium ion battery right here. Go ahead and connect that. See how that runs. And I think this only uses, say, 2 amps. So nice little 6 8 watt Tesla coil. Right, looks good. Yeah. Come on, stay connected. So yeah, quite a bit of power out of those SOT23s. They don't really generate that much heat. You get a decent functioning Tesla coil with them, surprisingly enough. I'm rather impressed with that. Rather impressed with that. Here's another modified ZVS driver Tesla coil that I put together. It stands 55 millimeters tall. Has pretty good performance too. That's just awesome. I'm going to go over some practical design tips. They may help you when you're making your own modified CBS driver Tesla coil. I'm going to split this up into 3 sections. The first one will be working with through-hole components. The second one will be working with SMD components that are designed to get a lot of their heat out through soldered connections. And the last one will be working with small outline transistor technology. Basically parts that are too small, too fast to really generate a lot of heat. So let's talk about through-hole packages. So here's the driver that I made using the ubiquitous IRF Z44As. Pretty good MOSFETs, but they're not all too fast. So if you're going to use those for a Tesla coil, make sure it's bigger than the ones that I've shown you on this video. Bigger means slower, and these will work for a much larger, much slower Tesla coil. Here's my board. You can see that I have the sources of the MOSFETs here. Gates are connected to the diodes in the middle. They're kind of hidden underneath the inductors. I've got my positive here, connected to the diodes. My gate drive transformer. But this is a pretty good design. It's flat. And most importantly, you can replace the MOSFETs when they blow up. Oh yeah. All of these designs, it's very important that you have access to the MOSFETs, because if you're just getting into making your own Tesla coils, or you're just like pushing extremes, you're going to blow up a lot of MOSFETs. So make your MOSFETs serviceable. But yeah, not a bad design. These heat sinks are also isolated, so that's nice. But yeah, that's what I did for through-hole components. Let me show you my favorite design, and that is for the surface mount components that are designed to get their heat out through soldered connections, the SMD, like the D-packs and stuff like that. So I have my heat sink. I have one of these sides from a thermoelectric cooler. It has my MOSFETs on them, and I have the top PCB, and the electrical connections are actually made through these screws. You see these diodes here, so that would be a MOSFET gate connection here, my positive connection, MOSFET gate. These are the outputs going to the MOSFET drains, and then this is my ground here to go to the MOSFET source. So let's take it apart. I'll show you how it looks. The heatsink and assembly is held together by these copper bars. I'm going to go ahead and take that off on the one side. Alright, and I'm going to remove the screws. Alright. With the screws taken out, I can take that board then, lift it up. There are my MOSFETs. Remove the entire assembly like that. So yeah, I have access to the MOSFETs if I need to replace them, which is nice. And the aluminum ceramic does a pretty good job of passing the heat from the MOSFETs into the heatsink. I'm also going to point out another thing right here. You can see that I slit the heatsink. Do that if you're doing this design. Otherwise, the eddy currents that will be induced into the heatsink from the primary coil will just heat up your heatsink, and you lose a lot of your Tesla coil's performance in inductively heating the aluminum heatsink. But yeah, nice design. I like it. And that's the design that I actually use. And there. Works real well. And now let's talk about the tiny Tesla coils. Alright, so you can see my little SOT23 MOSFETs. Got my 2 inductors here. Here's the source, so that's negative. And here, and here, and here, I have little pieces of wire that are acting as vias. So the gates of the MOSFETs go to the other side of the board, and that negative connection goes to the other side of the board. take a look on this side. I have my positive, which the other side of the inductors are connected to. My little gate drive transformer right there. I have the 4 diodes. Here's the turn on resistor on one of the MOSFET gates. And I have my negative rail here. And the ground. So yeah. Pretty nice design for a little Tesla coil. So it works pretty well too. It'd be a nice way to end this portion of the video. But hopefully, seeing what I put together gives you some insight on how to design yours. No, that's not a good sign. Something is wrong. What are you doing? Oh, hey, it was working. Bad connection. Pretty feisty little coil. Pretty feisty little coil. Later on in the video, I'll be discussing interrupter circuits and how they allow us to take control over the output of our Tesla coil, just like this. But first, a few words about Tesla coil accessories. Let's go over some easy to find and make accessories of which will help turn a simple Tesla coil like this into a more fun learning experience. It's a pretty warm day today, so if you guys don't mind, I'm going to put on a fan while discussing some of these. Better. Much better. Alright, take out a Tesla coil. Plug it in. Now, if you're just getting into Tesla coils, I want to recommend that you get some fluorescent bulbs like this. You can use this or bigger, but fluorescent bulbs really do have a low activation energy level and threshold, and you get a lot of light for a little bit of energy. So these are pretty good. Turn off the light. We can see we get a decent amount of output. You can also get black lights, which are pretty much the same thing, except they don't have a phosphorus coating on the inside of the tube. And in general, black lights are pretty cool by themselves. So go ahead and pick up one of those. Pretty fancy. You make you make the other tube glow. Pretty fancy. But yeah, fluorescent bulbs, definitely, they're good for testing Tesla coils too. See whether they're working or not. Earlier in the video, I showed off this little fluorescent bulb right here. I'm going to go ahead and put it in. Like that. A pretty nice little fluorescent bulb. I'm going to show you how I made it. Let's say you're looking for a little fluorescent bulb like this. Well, say you have a longer fluorescent bulb, such as a cold cathode fluorescent pulled from an LCD TV or a monitor, like this. We're going to go ahead and see if this one works. You light up. Okay, yeah, there's a little light there. So this too works. So you want to make it shorter. I'm going to show you how I did that. And you probably shouldn't, but overall, it's actually really safe. So no worries. It will involve fire though. You're going to need a little mini torch like this. And we're going to light the torch like this. And we have flame. Alright, so what I'm going to do is I am going to heat up the area which I want to take off very carefully. And I find that if you grab your pieces by the ends, they work a lot better. Now I'm going to go ahead and once that's liquid, I'm going to twist a whole bunch of times. And you need to do this so you form a good seal. Just like that. Wait till that cools down a little bit. It usually cools down within a couple of seconds. Yeah. Alright, I'm going to come over here now. I'm going to take off this section. So the same thing, I'm going to go ahead, give it a bunch of twists. That way I get a good seal. There you have it. A little tiny fluorescent ball. I'll go ahead and see if this works. And it does. And that's how you make your own little fluorescent bulbs. Pretty cool, eh? Pretty cool. Another neat thing that I did involving the tubes is that I put little fluorescent lamps and neon lamps inside. And one of the things that really does help with making these is that you have some of the wire from the bulbs sticking out on the ends. So I have that loop here, that loop here. It really does help make them both glow nice and bright. It's very simple to make. Not much to them. Not going to bother making one for you guys on camera. I'm sure you can figure this out. But these light up pretty nicely too. No problem. One of the things that I was messing around with was another secondary that I had from something. Not sure when I made this, but messing around with how an LED would respond to the electric field when there was a coil on it. So I decided to take the idea and do something very similar. For the little tubes, I made smaller coils, just like this. And on each end of the coil, so there's an end here, and that's twisted on the purple wire, and this end here, twisted on the white wire. And I put the twisted side on the cathode of the LEDs. So the LEDs are backwards to one another, and they both light up because this produces AC, so half the cycle one LED lights up and half the cycle the other one does. But at about 1 megahertz, they both look like they light up at the same time because our eyes don't see that quickly. Go ahead and show you that. That's very focused. Very focused. There we go. Oh yeah, that works pretty well. And of course, that's what led to me making these tubes. And you can make them any color you want, depending on the LED that you have. Put that there. They're very nice tubes. They really do bring a whole little kit together. And with different colors, you can select also what kind of color combination you want for your nightlight. That's pretty neat. Some other interesting things that you can use for Tesla Coil accessory. And you don't have to limit yourself to just gas discharge lamps like this. You can also get incandescents to light up. So, for example, here I have another coil with a little incandescent on it. And I can get this to light up too, which makes a fun accessory. Let's see, squeeze the wire a little bit, that way it stays on. There we go. And you can just set to what brightness you want it. Oh, it's pretty bright actually for a little bulb like that. You can set the brightness to where you want it. That's neat. Now I'm going to show you what could be a really cool Tesla coil accessory if you choose to make one. That is another Tesla coil. But watch this. It's where it gets pretty interesting. Now, of course, because they're roughly the same size, they will transmit and receive quite efficiently. I'm going to go and unplug this Tesla coil here. And I am going to put this Tesla coil close to the other one. You can see that lights up a little bit. I'm going to go and tune the frequency of that Tesla coil. And to do that, I'm going to go ahead and clip these on ground. And you can see the more energy I draw off that one, the slower the fan up here goes. Take the fan off. There you go, brighter yet. Turn off the light. But yeah, so this Tesla coil's not plugged into anything. And of course, that's dependent on how much I change the frequency and ground that out. But yeah, I thought that was neat. And what's really neat too is if I take this incandescent bulb, I put it around here, doesn't light up, doesn't do anything. Unless I put it physically on the coil. Then it will light up. But if I have another Tesla coil here, I can light it up again. And as I said, this is not plugged in. Not plugged in anything at all. But it's picking up the energy from the other Tesla coil. And it gets even more strange too. It's really fun. Seriously, make 2 Tesla coils. They're really fun. So, if I move my hand by the coil, you can see this LED right here gets brighter and dimmer. You can see the output on this change as well. I'm going to take that off for the time being. I'm going to get this fluorescent lamp. Of course, I can light the fluorescent lamp over here on that Tesla coil. This Tesla coil here, not plugged into anything. Take it over here. I am going to now light up this Tesla coil using, light up this bulb using this Tesla coil. Like that. And it actually works pretty far away. Even though it's plugged into nothing. So that's interesting. And we can get it light up again. Yeah, that's cool, eh? So build a second Tesla coil. It has roughly matching to the other one. You can have a lot of fun with 2 Tesla coils. In fact, I didn't know this was possible. But it works pretty well. Want to light up again? Yeah, that is neat. That is neat. So learn to experiment, put some stuff together. Now, suppose I should show you the little fan real quick, because that's also neat. You have a transformer, and you can put more taps on a transformer, more coils on a transformer. So A Tesla coil in of itself is a step-up transformer, but you can also step down on it too, which is why I have these coils. And of course, to turn AC into DC, I have a little discrete full bridge rectifier made of four 4148s, little signal diodes. No battery at all. Now, sadly, this doesn't work. Not enough current. But yeah, don't limit yourself to just fluorescent bulbs. Seriously, make coils, experiment, make more than one Tesla coil, hook things up to things. You can see some pretty interesting results if you play around. I've been having tons of fun with these. And now on to what is probably the most difficult part of the video, discussing Tesla coil interrupters. That's a pretty complicated topic, so sorry if this is confusing, but I'll do my best to get some good information across to you, and hopefully this will help you build your own. So first of all, let's talk about why you'd want a Tesla coil interrupter. Well, they allow you to do a couple of things. First, they allow you to, control the general output power of your Tesla coil. They also allow you to control the burst frequency, so you can actually generate audible tones. And you can also use it to inject a square wave from an audio source, say like a piano or a converted audio file, and you can turn these into musical Tesla coils. Now, besides that, there are practical reasons to have an interrupter. First practical reason is they allow you to get all the arcs and sparks without drawing a lot of current, because it's not always operating. So for example, you'd have very fast output spikes, and you'd see the output spikes, but because the Tesla coil is running at such a low duty cycle or frequency, it'll practically do that all day while consuming very little average power. Second thing is it keeps things pretty cool because you're not using it all the time. So your primary stays cooler, switching transistors stay cooler, everything just stays cooler, which of course is good because the biggest killer of electronics, as we all know, is high voltage and heat. Um, and it also allows you to cut down on some other problems too, such as the issue with having high frequency corona build up on the primary or on the inside of the secondary. It tends to be a little less of a problem when things are running cooler. When things get warm, you have a higher risk of generating that. So it just it helps. It really does help make your Tesla coil run cooler, more efficiently. Not more efficiently, but you get more bang for your buck. Yeah. So let's talk about what an interrupter is. And we're going to first discuss why it's called an interrupter and not simply just a Tesla coil controller. So both of these are self-resonant systems, and I discussed earlier in the video that you need to have a resistor to turn on the transistor, whether it's a MOSFET or whether it's just a general bipolar junction transistor. So, for example, in Slayer Exciter, we got this 22. Well, 22K. Well, as I said earlier in the video, the secondary starts oscillating. There's a flipping bias on there, a changing polarity. So half the cycle this is positive, half the cycle this is negative. When it's on the negative side of the cycle, it turns off the transistor. When it's on the positive, it turns on the transistor. And you need to have a kickstart from the positive rail to turn on the transistor the first time. After that, it's a self-oscillating circuit, so it's going to make its own positive on the next cycle as the secondary rings, and it's going to turn it on and keep the oscillating going, even though you don't have the resistor. I can actually show you this. Let's put this aside. So what I'll do is I'll take this, go ahead, I'll plug it in. See the blue light? You can see the fluorescent light up. Now, being very careful not to short anything out, I'm going to pluck out the resistor. And you can see that resistor right there. That's 22 kilo ohm. I'll pluck that out using an insulated tool because I want to not short out the transistor and keep it oscillating. All right, so there it is. Transistor has been plucked out. Resistor, sorry. You can see the LED light is still on, and it's still going. So it's generating its own positive turn-on signal at this point. That the only way to stop it is to interrupt the oscillation, and do that simply by touching the coil and taking all of its power. And there it is, it's off. Now it won't start back up until we give it a new turn-on signal from a positive source. So the interrupter does two things. Not only does it provide a turn-on signal at the right time, but when it's not receiving a turn-on signal, the base or the gate of the semiconductor needs to be quenched. It needs to be turned off and actively pulled down to ground, which is part of the reason why I call part of the interrupter the quencher, and the other part the PWM generator. Let's take a look at one of the quenchers that I put together. Now this has two outputs, so two quenching outputs and one positive signal output. So these are both N-channel MOSFETs. This is a P-channel. These provide the pull down for the gates, and this is the turn on signal. And the resistor needed for that is right here. In this case, because I'm going to show this one on a Slayer exciter, that's a 22 kilo ohm resistor. And because we're only pulling down one semiconductor component, we can go ahead and ignore this MOSFET entirely. Focus on these two MOSFETs and that MOSFET. Let's go ahead and draw this out. All right. So here's a diagram of the Slayer exciter. Go ahead and draw a simple interrupter quenching circuit. And once again, this not only provides the signal, but also provides the active pull down to stop the oscillation. Go ahead and draw the N-channel MOSFET. Draw that up here. So drain, gate, source. Let's go ahead and label those D, G, S like this. So that's the N channel. Go ahead and draw the P channel for the turn on signal. Like this. Same pin out, so drain, gate, source. The P channel actually gets connected positive, so let's go ahead and draw that positive rail right there. There's also another N channel MOSFET in the circuit. And that's to take the positive and convert it over to a negative. You pull down the circuit when needed, and to turn on the positive. All right, so draw that there. Once again, same pin out, gate, drain, source. All right. So we need to control the two gates up here. The two gates are connected. When the gates are positive, the N channel is on, and it's actively pulling down the semiconductor in the resonator. When it's negative, that means that we have a positive signal from here, and it's on. So it's providing the pull-up potential from whatever ground reference there is. So go ahead and attach these two gates together, because they are a common connection. Now, when the circuit isn't running, you want to have a pull down signal to quench the semiconductor. So on this side, we're going to need a resistor. Let's go ahead and draw that. Going to positive, so that way the N channel is on. Draw that resistor right here. That'll be a 10K. And then we're going to have to control this somehow. Now that's controlled by the N channel. So when the N channel is on from a positive signal, it'll override the pull-up. It'll turn off the N channel here and turn on the P channel because it's grounded. So that can get drawn up like that. And then the two sources of the N-channel MOSFETs. They're both on the negative rail. So go ahead and draw that in the diagram. So over there, and then there. And since we want to have this off when it's not getting a positive signal, which will keep the this on and keep this off, we're going to have a pull-down resistor on that MOSFET as well, between its gate and source. And that once again will be another 10K. All right. So there's our input from the PWM. Here's our power. And here's our ground. In this case, we can actually attach the two grounds or negatives together. So let's go ahead and practically do that on the diagram. Like this. Down. And then we can attach together the two positives. So I'll bring this up here, run this over, up to positive like that. Oh, we need to connect these together. All right, well, we'll do that too. We'll do that through that resistor. So because we're using a 22K to turn on the transistor down here, and this is now where we're getting our new positive pull-up signal from, P-channel MOSFET here, we're going to go ahead and get rid of that 22K resistor because we don't need it. We're going to run this up like here, jump like this, up to here, up to there. We want this directly connected to the drain of the N channel because it needs a hard pull down. But from the positive, well, that's where we connect the 22K in that point. Just like that. Now whatever power we feed in here powers the entire circuit. And then whatever we put between negative, in this case ground, and the on, the gate of this N channel MOSFET here, now we can control the circuit. So I have only drawn the quencher part. I have not drawn the PWM generator. Take a look at a PWM generator real quick. The first one I'm going to show you is a simple one made with a 555 timer. And the circuit that I'm using is just for the flyback transformer driver. So this will power a single MOSFET. So yeah, and that'll put out a positive signal. But anything you can use to control an N-channel MOSFET or any kind of positive signal output you have, whether it's from a musical device, a PWM generator, like this, whether it's from a piano, anything, that positive signal to turn on that MOSFET is what you want. But yeah, so all this does is it generates a positive output. We can see that positive output on the LED, positive signal, and that'll be represented by the LED turning on, turning off. This portion of the video will probably contain a lot of flashing, so be noted of that. Got my power input wires here. Let's go ahead and turn it on. We'll mess with those two potentiometers. All right. Now, the flashing you see here is not representative of what I'm actually seeing. That's because of the shutter rate of the camera. It's actually going much quicker in person, but you can kind of see how I can change the speed of the flashing, and I can also change the overall brightness. But again, that's not truly representative. Let's see if I can get it to kind of sync up here with the speed real quick. All right, hopefully you can see the intensity. So brighter, dimmer, but you can see that we have a circuit that generates an output. So part of the signal here, got a common ground wire here, which will attach to the ground in the circuit. To actually go ahead and now interface the PWM circuit with the quenching board. To do that, I am going to take You got the positive and negatives here. I combine that with the positive and negatives on the PWM circuit. Just like that. These right here will go to the input of the MOSFET there. So positive, shared signal ground. It doesn't have to be, but in this case, it is. Go ahead and solder that on real quick. All right. Now, I'm going to connect both of these together, the PWM generator and the quenching board. There's a little LED on here, which is controlled by the output of that little N-channel MOSFET, that first one, and then to the positive rail through a resistor, the 22K resistor. It just helps indicate whether or not things are connected properly, as most indicator LEDs are. So connect this up, and we'll see the same flashing here. We do here. So that tells me that the quenching board is getting a signal now, and we should be able to use that to interface with the transistor, because now this is not only getting an active turn on, but getting an active hold down as well. So you have a little hook here that'll go right into the socket where the resistor was on this Tesla coil. I'm gonna go ahead and turn off power. All right. Oh, I just realized I need another JS connector. All right, got one. All right, so I'm gonna plug the Tesla coil into the same power as everything else is here. So negative, positive, and I am going to try to carefully plug in our interrupter to the base of the transistor. Boy, that's not staying as well as I wanted to. You know what? We'll solder it. Look good. All right. Let's turn everything on. And now you can see that you can't. All right, well, you should be able to see how the bulb is now flashing. And I can control the flash now using my timer circuit. So hopefully that explains kind of what an interrupter is, what an interrupter does. Next, we're going to install an interrupter in this Tesla coil, see how it performs. Let's add some features to this Tesla coil. Now the first thing we'll need is another diagram. So here on this portion, I've drawn out the entire modified zero voltage switching circuit, a self-resonant circuit that actually drives the primary and gives us our high voltage output through the secondary. And that is already, as we know, driven by the polarity on the base of the secondary that powers the gate drive transformer. and that puts a positive or negative potential on each one of the MOSFETs that switches in polarity as the system resonates. Now, in this circuit, we only provide a turn-on signal to one MOSFET just to get the system to start oscillating. Once it's oscillating, we don't have to worry about providing an odd signal to the other MOSFET because it's already generated by the secondary through the gate drive transformer. And that is why on the quencher, we only have one pull-up. So we have this P channel that provides the pull-up through the 5K resistor onto this N channel drain right here. And we have the two N channels, which when they're active, they pull down each MOSFET gate to negative. So they quench. So we have one turn on and two quenchers. And this is the quenching board that I showed earlier. So that's this. So we have to interface this with the actual resonator circuit. This is very simple, and we do this almost identical to how the Slayer exciter circuit was interfaced with the quenching board. So we're going to disconnect the resistor right here because we don't need that pull-up from positive. And then we're going to connect that to the quenching circuit. So we just take this side right here, because that's through the positive, through the resistor. And then we connect that side to the base of that gate where it was connected to the resistor here. Now we just need a active quench on this MOSFET gate. We don't have to worry about providing an on signal. So that's what this low and N channel MOSFET does. We'll take and draw a connection like this to make it less confusing over and on that MOSFET gate like that. I'm also going to connect the quenching board up to the same voltage rails as I do the actual modified zero voltage switching oscillator circuit. So just like on the Slayer exciter, I'm going to connect those as well. So we'll have this connection like this down to negative, and I'll join the two positives together as well. Now I'm going to have a little mystery box, which will be my PWM generator. And I'm going to draw that mystery box here. That itself will have its own positive and negative input wires. So I'm going to go ahead and draw that. Drawing at a funny angle. And then let's say we're going to have our power input right here. And then from here, we'll have a positive output signal that's going to go to the gate of the N-channel MOSFET on the quenching board to turn it on. So I'm going to go ahead and I'll use orange for that pull-up signal. Like that. And then we'll have a redundant shared negative connection. It doesn't really matter because already all the negatives are connected, but I like to be just extra precautious and do a redundant negative. We'll treat as our signal negative. So yeah, that's it. And then on this we'll have our little potentiometers we can use to change what the Tesla coil is doing. So here's my little mystery PWM controller. It's a little 5556 timer. And the circuit is pretty much encapsulated in epoxy. And I can remove the chip in case the high voltage blows it up. But I haven't really blown up one of these. So it looks to be a good, robust part for this. And I'll also put up some build pictures at the end of the video in case you want to see exactly how this was put together, but I don't have a circuit diagram. Maybe JP can do a video on how to make the interrupter and full Tesla coil. He's the one who showed me a bit of this, so He's a master. Anyway, let's go ahead and connect this up to the Tesla coil. First thing, I gotta open the Tesla coil, gain access to it. Alright, now that the Tesla coil is open, first thing I'm going to do is I'm going to install the quencher. So on one side of this board, I'll have a resistor from the positive to the MOSFET gate. And you can see it kind of right in there. Actually, I'm going to disconnect this one side so work with it a little easier. I should probably lengthen those wires, but you know, I'll do routine maintenance and adjustment to the physical build once it works and doesn't blow up. All right. So there's that resistor right there. I'm going to remove that resistor and I'm going to replace that with the one side of the quencher that has the pull-up resistor on it. All right, so there are my two outputs from the quenching board, and those go to the gates of the MOSFETs. Now I have power and I have signal, so I'm going to go ahead, trim those two wires down, and connect them to the leads of the capacitor there. Now I have the output signal wires for my PWM, and I have my power input wires. And so we'll go ahead and connect those up. Now let's see how this will physically go together. You probably want those on the back, and I'll change the location of the capacitor over to the side later. Yeah, for now I'll run it out this side. I'll keep the wires a little longer on this because I don't know exactly where I'm putting it. And then power wires. Go ahead, cut those to about here, and I'll put them on the base of the capacitor as well. All right, it's electrically together. Aside from the other wire that goes to the primary. Go ahead and solder that real quick. Give it a test. See if MOSFETs explode. All right, looks good. I'm gonna turn on the power, connect it up, see how it operates. Now, as I said, it could break a few MOSFETs, but they make more. All right, limit it to 2 amps right now on the power supply. Plug it in. Hey, I know what that sound is. right? Looks good to me. Well, let's play around with it. Turn off the light. Get my turn pot tool. So that's power output. And let's try frequency adjust. Looks like it works by me. This will be a nice little Tesla coil once it all gets put together. And now to show you my favorite Tesla coil, the Titan of my collection. In fact, at 100 millimeters tall, it's the tiny Titan of my collection. Now the tiny Titan has a little bit of a backstory and was developed by my friend JP, same person who posted up the video about the modified zero voltage switching driver for running Tesla coils. And he and I did the YouTube channel Join the Technicians together, and we did a couple of other high voltage gizmos, such as the plasma pens and the magic wand. But this thing performs astonishingly well for its form factor, probably why it's my favorite Tesla coil. I'm going to go ahead and plug it in. I'm going to be running it off of 10 volts. All right, turn it on. And I'm going to turn off the light. Give you a little bit of a spark there, but just watch what happens when I turn this up. So, a little bit. Go crazy with it. I have never seen so much power come out of a small Tesla coil like this. This will also allow me to show you my personal favorite Tesla coil accessory. I'm going to go and turn this off real quick and show you that. Off to the side. Separate the power wires. Surprisingly enough, my favorite Tesla coil accessory, and you should look for them too, incandescent light bulbs. Now, they have different ages and different atmospheres, mixtures of inert gases inside, and you can get some pretty good results. In fact, my favorite are the appliance lights that you get, and they're incandescent lamps that run in like stoves and stuff like that. And they are appliance bulbs because, well, LED's not going to last very long in a 400-degree stove oven. But but yeah, so I'm going to show you some incandescent lamps. All right. I get both cards out. These things are a dying wonder. So I'm going to turn on the Tesla coil. I'm going to figure out what. Okay. All right, turn off the light. take a look at some of these. Zoom in. And not all of them light up. Oh, that's a good one. Right. Oh, the PWM. All right. Oh, that purple not showing up very well on camera. That's a shame. Show you some more. Take off the needle. There you go. Put some other bulbs on there. Quite nice purple off that one. Same one on there. See if I can get a better view on that if I turn down the power actually. Some of these light bulbs will also work on the top of Slayer exciters and make little itty bitty plasma globes. So go ahead and try that out if you have some incandescents laying around. Let me take a look at this one. And I'm going to show you my two favorite bulbs for Tesla coils, and prepare yourselves to appreciate the incandescent light bulb all over again. So these two bulbs are just normal appliance incandescent light bulbs. Yeah, these things are cool. And for my favorite, it has a little bit more color in it. And I love the green that I hope comes across in camera a little bit, but it is hard to capture. A very dim green. I'm going to show you that. It's a little bit more orange than the other one too. I'm going to turn off the light so I can get that green. Yeah, that's just a beautiful beautiful light bulb. Oh yeah, you see that green in there? At last we have come to the end of another long video, of which I hope you have enjoyed and has taught you a bunch, of which will help you build your own DIY Tesla coils. This video was really geared towards showing you how the parts work and how they interact with one another, which is vital information when you're experimenting with different configurations and components. The goal really is to get you comfortable with playing around with different components, and playing is supposed to be an enjoyable process of experimentation. That's what my friend JP said. He says, never forget to play, which is vital life advice. Well, that's it for this video. I hope you enjoyed. Stay tuned for more.